I guess I will record this. If I feel like uploading it, I'll upload it. If I don't, I'm just gonna delete it and just leave it there. But yeah, yeah, just for the video, it's really unstructured, so I'm just gonna ask people what they want and then go from there. But if we don't have questions, I'll just go over the lectures for Wednesday and Friday. Yeah, yeah, yeah. I think like so when you guys do pentose phosphate, like some of these will come back and like you won't have to remember them as in depth, but they will show up for the final, right? Because like the finals, it's weird because the finals like cumulative, right? But like I remember for my final, the only thing I remember from my final was the insulin question. I don't know if anybody's looked at that exam yet. I know you guys have. There's a question on my last exam, which yeah, I wouldn't say it's that important to look at it right now. What I remember from my test though for the final is the only question I remember is the insulin question, where they gave you like an SDS page diagram and they asked you to draw every single line for like or like which SDS page thing. Yes, yeah, yeah, dude, that was so horrible. That average was like a 50 something. It was so bad. Yeah, that was my final, but there was like nothing else on the test. That's the thing. Like that's like the only thing I remember from that exam. I think everything else was like fine except for that. That one was horrible. I remember like oh god, I think I used to have like a friend who scored like a 28 on that test. It was so bad. Um, but yeah, any other questions about content before I just go gapping into oblivion about anything you've learned so far, stuff like that. Not really. Okay, cool. I guess we can just go ahead and like just see how far we can get through like your lectures for Wednesday and Friday. Do you guys have questions on the lecture for today?
Let me just try to basically summarize.
Yeah.
Like, actually, all I remember is there's like this critical photo system, right?
Yeah. So PS1, PS2, yeah.
Yeah, and the one that accepts them as electrons is like 680 or something, right?
Yeah, the specific names for them.
It's like,
Yeah, so let's see if we can find the nice diagram of it. Because even like 'cause it's been so long since I've looked at these, like it's been a while, basically. But like, yeah, so P680 here. This is photo system 2. Where is photo system 1? I think they discovered 2 first, actually, which is why the photo system 2 is actually the first one, and photo system 1 is the second one. But do they yeah, okay, here we go. Yeah, so photo system 2, yeah, so P680 and then P700 for photo system 1. Does this kind of make sense? There's a lot of stuff going on here. Yeah, it's basically ETC, but now you're in a chloroplast, right? So like I also want to make sure that we like understand that like mitochondria are still in plants. Like plants still do like the whole mitochondria stuff, right? There's just a separate organelle that does this nonsense, right? Um, but it's kind of like the opposite of what um mitochondria do, because what mitochondria do is they take electrons from like NADH and all that stuff, right? And then they reduce the oxygen into water, right? This is the opposite, where it takes electrons from water, right? And it like goes through this weird cycle, and then the whole point of this is one making NADPH, which is used in the Calvin cycle, if I'm not mistaken, and also like producing ATP, so that they're making like more ATP in a way, right? And the other thing that you guys that is kind of weird about this is like the the diagram of how this works, right? So like for mitochondria, right, ATP synthase, basically you're pumping protons into this space, right, to then shuttle them back down into this space. But in plants, it's flipped. Yeah, it's flipped because instead of you're now I can't remember, is it the thylakoid lumen, I think is what it's called. You're basically pumping protons into the lumen to shoot them out in this direction instead, into the stroma, which is like the opposite of what you're doing in the mitochondria. And I'll cover this more in depth when I do my like actual like lecture video. But I believe they asked a question on this on my exam. I can't remember off the top of my head. There was a weird question I remember about like the directionality of the ATP synthase and stuff. But they could totally ask you like where is the CF1 and where is the CF0 in like the two cycles. right? And you'd have to, so the CF0 is like always in the membrane, right? But the CF1 switches, right? So because the CF1 here is in the stroma, but in the mitochondria, it's in the matrix, right? So it's just something to be careful about. But like I think what I want to like say here is this whole thing of water. We basically take electrons from water, um, and we're using this light to like excite it and like fire a bunch of energy into it, and then that goes along, right? Goes through the Q cycle here, um, goes through this, right, and then goes through PS1, and these are all like um, different like electron carriers within these photosystems, and then it eventually all goes into NADPH, right?
We should care too much about the
The individual carriers. Um, I would say that, like, generally speaking, you should have an idea of which ones have higher reduction potentials than others. I wouldn't say you have to memorize every single one of them, but like you should know, like, oh, do cytochrome A's have higher production potentials than B's and then C's, right? So in this case, um, if you look at here, like in this case, right, you would expect that cytochrome B has a lower reduction potential than like P700, for example, or something. Because like the fact that the electrons are being transported from here to here suggests that it's favorable to do that, right? And so I would expect this to have a more positive reduction potential, right, compared to cytochrome B. Just like general relationships is kind of important.
which second select
The Q cycle is generally similar. Yeah.
plus or not set up.
Yeah, it's relatively similar. Is there a slide on that real quick?
I think no, it's on the oxidation.
Yeah, it's on the previous one, right? I already did a video on that. Did they say it's 4 electrons?
Yeah, I guess it takes 4.
Yeah, I guess it would take like
It will take 2 electrons.
yeah, I guess it's basically like doing the one that thing I talked about before where it's like you get QH2 and you do like a weird radical thing where like one goes up, one goes down, right? The one who goes up just goes away, right? Another Q comes in, radical, radical, right? So now you have 2 down here, and the one that was up here now goes to the rest of the chain, and now the 2 that you stored before go. Does that make sense what I'm talking about? It's weird. Yeah, let me. So it's I guess like when I say 4 electrons, like it's 4 electrons because we're storing 2 and then releasing them, right?
The bottom is fucking QH2. The bottom one, the top one is like we're like getting the off space right?
Yeah. Yeah, it's kind of like strange here. Let me go ahead.
All those electrons are used in the cube
Bro. Oh shoot, wait, I just realized I already have that.
complex 4.
For what? Sorry?
The 4 electrons are on
From complex which one? Yeah, from complex 3.
2 electrons. 2 4 protons now.
I mean, it does though. It takes one from. So I mean, there's 2 electrons that go through,
Yeah.
right? Because one of them goes through cytochrome C. Like here, let me see if I can find it. Where is the Q cycle one? That's not it. Where is Q cycle? It should be. How far down is this thing? That's ATP synthase. I think I passed it. I definitely passed it. Where is Q cycle? Is it in the previous lecture? Really? Damn. Is it in 23? Oh my god, please load. Oh, I guess it would be in this electron transport. Where is it? Yeah, like so like this diagram is what I try and memorize basically. Here. Let me go ahead and do this and like so like see how like it starts like very like negative. It's like this wants to give up electrons. So FES and FMN, right? And then FAD and FES, and then the cytochromes, and then so like you can see like so B C, and then A, right? That's kind of like the order I would kind of try and keep in mind, basically. And then like this is not important. I'm gonna be so honest with you. They're not, if they test you on the specific structure of this iron sulfur protein, you much might be cooked. Like, yeah, no, they will not test you up. No, that's some next level bull. Okay, like they should not be testing you on that. Yeah, so this stuff. Okay, I actually drew a bunch on this, but like if you look, so like yeah, so Q pool, right? We have a QH2. One electron goes here. One goes into cytochrome C, right? And then this cytochrome C, sorry, right? And that gets shipped into the next complex, right? Into complex 4, right? Because if I'm not mistaken, cytochrome C can only carry one electron at a time, right? Which is different from ubiquinone, because ubiquinone carries two, right? So another thing they could easily test you on. Actually, that was on my MCAT. Funny enough, how many electrons does this cytochrome C carry? And I got it wrong because it was on my practices. It was on my practice exams. Yeah. No, it was on my real one, but it could show up on your real one. So yeah, they do ask some stupid questions sometimes. But yeah, like so 2 electron carrier versus 1 electron carrier. And like this mechanism makes sense generally, right? Like we understand what's going on here? Sort of like we just have QH2, 1 electron goes up, and then this gets shuttled away, and then this goes down, gets stored here, right?
The two electrons from the is it two electrons, one of the QHs?
What do you mean?
When NADH gives electrons, right?
To QH2, yeah.
Yeah. So wouldn't that be the NADH's QH2?
This? Yeah, it would, right? But then like one of those electrons goes here and the other one goes to the rest of the cycle, right? Right. So basically, like if you were to try and track electrons, I don't know how you do that. It's like not possible, right? But like if you were to track electrons, right, and you were to go here to this state right here, this QH2 has electrons from 2 different NADHs, right? It's not the same NADH. And then this cytochrome C would give complex 4 2 electrons from 2 different NADHs, right? Or 2 different FADHs, whatever, or FADH2s, whatever, right? Right? Does that make sense? Right? It's not the same NADH giving its electrons to both, right? And then
Wait, so what would you say one NADH creates four proton from complex 3?
what do you mean? Why do we say that? Um, so each we should not be thinking about NADH as the one giving the protons, right? We should be thinking about the pumps as the ones that do the protons. You can think of it as like 2 electrons for 4 protons, right? But then that kind of falls apart when you're looking at FADH2, right? Because FADH2 only pumps 6 protons, right? Does this sound familiar? Because if we remember, right? Because it goes to, and I don't know why they just deleted complex C from these images, but um, like if you look at complex 2, I've drawn a bunch here as well, right? What the main thing you should like remember for sure, if I was to say, is like this is 4 protons, right? This is this is 2 or 4. Okay, I'm actually kind of forgetting now how many this is 4 as well. One of them is 2. This is 2. Yeah. So like FADH2 like also gives up like I'm pretty sure 2 electrons if I'm not mistaken, right? But the issue is like where it's being deposited in the ETC, right? Because like if it's being deposited into complex 2, we're missing out on this 4, right? And then we're only getting these 6, right? And then through a bunch of experimental nonsense, right? You can try and you can figure out that the ratio of protons to ATP is like 4 protons per ATP, if I'm not mistaken. Um, there's like a nice little diagram of how they drew it here. Let me see if I can like duplicate my tabs here instead of having to open all of them at once, you know? Yeah, there's like some weird like conversion but I'm trying to like remember off the top of my head, but believe it or not, I don't remember. So, uh Where is where is it? I swear he wrote it in like red.
Yeah, I thought that.
Yeah, yeah, here, yeah. So this is like the gold standard of what you should remember. And like I don't remember if they asked a question like this on my test, but this is probably like the like one of the easier questions they could ask about like I think this is like relatively straightforward. It's just like can you do math? The answer is mostly no, because I can't do math at this point, and I've just lost the ability to do math. But like, I think the thing you should know is like this is 10 H pluses, right? I probably should have just kept it, and this is 6, right? Oh, he for sure will ask about uncouplers. Oh, for sure. I don't know if he's gonna make you do math on that though, because like the math for that is like it's way too like prediction based. It's a little bit. It's not like the enzyme mechanics, right? Where you could just like say, oh, here's an inhibitor that like makes your cam 10 times larger. This is like if they give you like an uncoupler, you have no idea like how much it uncouples it, right? You just know that it affects the amount of ATP, right? So they can totally say, "Oh, you've added DNP. What happens to ATP production?" And you have to say lower, right? Or like they can like totally ask about different inhibitors. When I talked about my video was like, is there a slide about inhibitors? Yeah, it's like I think there's like a big slide that he did like with a bunch of inhibitors on it. Yeah. Oh, sure. Yeah, we can just look at those. Yeah. Do they not show up on here? Oh, that's crazy.
These are like this. These are going to be the same format as the exam questions.
Which two choices is why mitochondria stop consuming O2 at the end of this experiment?
Like this is what he wants us to do.
Yeah.
The polarity and everything.
Oh, that's so weird.
Exactly. I'm like, so it's not just like simple math. It's like, oh, there's polarity. You have to. There's like his reasoning was like, one pyruvate gives how much ATP,
Mm-hmm.
and then but how much ADP does that require? How much phosphate does that require? So,
Oh, that's so weird.
so one pyruvate, how many NADHs does that give? It's like
One pyruvate would give two
two,
NADHs, yeah.
and that no FADH, right?
No FADH2. Unless is this considering citric acid cycle as well?
I don't know.
Because if it's considering citric acid cycle, it's completely different, yeah. Because like if it's just glycolysis, it's just gonna be like um a single pyruvate. A single pyruvate is only gonna have one NADH, right? So if I have a glucose molecule, it's gonna go through glycolysis.
Wait, I think I remember the solution
Okay,
now. Okay.
yeah.
So it's 0.1 millimolar times this. So you'd make like 1.15 ATP.
Gotcha.
But this is only enough to make 0.5 ATP because you have 0.5 millimolar ADP and 0.5 millimolar free phosphate.
Gotcha.
So
Okay.
you would run out of ADP first, and then also
Yeah. Oh my
count
god.
electrons with the available NADH, so the gradient.
Oh, that's so
is two.
crazy.
Yeah. So
Yeah.
without
That does make sense. That's really horrible. Yeah.
he said that's basically that.
Oh my gosh.
Question?
The poll everywhere question, yeah.
Did you see the poll everywhere question? Which one? Yeah, it was like last lecture or 2 lectures ago.
Yeah.
Yeah.
Yeah, the O2 one. Yeah, that's a crazy one.
Yeah, it's not the graph. Yeah, the graph.
Yeah.
All that.
Does this make sense?
Both like this 5 to 0.
Yeah. Because you have you're basically saying that for every mole of pyruvate, you're producing 11.5 moles of ATP, right? And so if you only have zero point 0.1, like it's proportional, right? So if I have 0.1 millimole, like 0.1 millimolars of pyruvate, I'm gonna make zero point 0.1, like not 0.1, but like 0.1 times 11.5 millimolar of ATP, right?
Like just like one video line.
Hmm.
You say that like one point.
One millimolar of pyruvate makes 11.5 millimolar of ATP. Yes.
So how was this again to even say that?
That's kind of like the weird thing.
Big
Mhm.
what's out. create
That is yes, that is true, right? Because then if you do, trying to think about how to do this. No, that is true. You're right, right? So what you said 1 mole of pyruvate makes 11.5 moles of ATP, right? All you have to do is scale that down,
yeah, we're all
right?
filling bottles.
So if it's 1 mole of pyruvate makes 11.5 moles of ATP, right? By definition, 1 millimole of pyruvate should equal 11.5 millimoles of ATP, right? So now if you just divide everything by 10, right? It's zero point 0.1 millimoles of pyruvate equals 1.15 millimoles of ATP. It's the same ratio, yeah. I think that's why you can honestly like ignore all this weird nonsense though. But you know what I mean? Like this is important, like this whole like NADH and FADH2 stuff. But it's just this is stuff that you could like figure out with like the 2.5 ATPs per like NADH thing, right? Does that make sense?
I feel like it's just if I see that on an exam, I'm
No, you're not gonna think of that. Yeah, you're not gonna make the connection on that. No, that's like really. I guess now you know though. I guess right. Like I guess like if he does that, like you can see that on the exam. But that's pretty. Yeah, I mean, like at least he's told you he's gonna ask a question like this. But like that's
then like what is this? Like
yeah. Um.
di nitrophenol?
Yeah. So dinitrophenol is the uncoupler.
Okay, so no matter how much pyruvate you'll have, you'll always run out of fuel because you'll just always be able to
Yeah. I guess like what is? Did he explain what he means by run out of fuel, quote unquote?
like you'll run out of pyruvate.
Oh, okay. So like, yeah, I see. He's like putting up mitochondria in like a lone area and then like stuffing a bunch of pyruvate in it. Yeah. It's just like a case of like so the uncoupler, right? What does the uncoupler do?
Yeah, couples.
Uncouples what?
Uh, I think it's that thing.
Yeah, right. So what does that mean? What does uncoupling mean? Like you can describe the process as well if you want, but
So there's a triangle that takes the H pluses
yeah,
down into the matrix.
yeah,
Gradient is no longer
yeah,
strong
yeah. And why is that a problem?
because that gradient is what makes ATP out of, right?
Through what?
Through ATP synthase.
And ATP synthase harnesses that energy to, right? Yeah, right. So yeah, you're right. Yeah, I'm just trying to make sure I'm like quizzing you here. But yeah, you're right. Like, so the point of the ATP synthase and the gradient, right, is like the gradient powers ATP synthase, right? But then if you get rid of the gradient, ATP synthase is like I have no friends, right? And so like it just does not work anymore. So yeah, that's why you would end up dropping ATP. But that's if you saw that the O2 consumption like goes up by a lot, right? That's because the cell is now trying to ink it. The cell has no idea, right? There's an uncoupler, right? The cell just like does cell things. So the cell is gonna like say, "Oh my goodness, I don't have any ATP. I have to upregulate my speed of electron transport chain." Little does the cell know that the uncoupler is just screwing everything over, right? So the cell is gonna keep using O2 in an attempt to make more ATP, and it's just going to be completely useless because it can't make more ATP. Because the uncoupler is completely diminishing the efficiency of the enzyme. Right? Does that make sense? Yeah. Yeah, and there's like other like um inhibitors as well. Like it doesn't have to be an uncoupler, right? There was a lecture before um where I think he showed you guys like different inhibitors and where they inhibit. I would I would try and remember those.
All like carbon.
Yeah, like carbon monoxide. Yeah, like where it inhibits because like totally could ask something on that. Um, all they have to do is like, oh, if you put carbon monoxide in, what happens to ATP production? The answer just it just stops, right? Because like it's completely inhibiting electron transport chain. There's no pumping happening, right? It's different from the uncoupler because with the uncoupler you can still pump, right? But if you inhibit the whole thing, you just can't do anything.
It's carbon monoxide. The complex one.
I'm pretty sure it binds in the same place as complex 4 where oxygen binds because it's like a strong binder like similar to hemoglobin, right? Where it binds like that iron complex. So it does that. But yeah, it's rough out here, man. Yeah, I think why do I have like random programs just like opening? I got a virus on my computer, I swear. Um Just all a bunch of stuff that. Oh yeah, this trips a lot of people up. Surprisingly, like, I don't mean like trips a lot of people up. I mean like they make silly mistakes on the exam.
Yeah, it's weird.
Yeah, that was devious. That is quite mean. Now, granted, there are some of those questions are like one and done. You know it. Some of them are just like, what is going on? Yeah, some of those questions were so mean. I think if they had given you more time, that's a reasonable test. But you did not have more time. Like I think if you had 15 minutes more, I think that's a reasonable test. But 45 is rough. 45 is rough for that exam. Also, they like had very specific things they wanted you to know, like the NADH wavelength absorption. Very specific, right? And granted, I guess they yeah, I guess they yeah, I guess, but I guess they also like had like a similar thing in exam one with the tyrosine, right? With the tyrosine and the tryptophan with the 280, right? So I guess it's like a similar thing, right? But like still, it's really annoying, right? And like that's like those are like just like vibe checks. Um, and then like the NADH structure one is also a bit mean because there's so many carbons that move around and like if you don't know what you're looking at it can be so intimidating because it's just a massive structure. It's just like what is happening. um but yeah, man, this is it's crazy, bro. Did I download the exam or no? I don't think so. Yeah, when is your guys' exam again? Is it next week? Yeah, I'll do an exam review on Monday probably. Maybe, yeah, maybe I don't know. I guess like 23 test, the 23 one. What's this one like? You guys didn't cover this. Oh yeah, no, I'd be down to. Yeah, this is so important. Yeah, but yeah, this is a thing where I'm just like yeah, it's just like a structure similarity question. Because like this one like because like for example, if we go back to my exam, right? Yeah, it's like this. Yeah, look, like, where is it? I guess they kind of tell you, right? But yeah, hold on. I look at this now. This is such an easy question. This is this is such a. I guess like if you didn't know the structure and the name, you'd be screwed. But like, I think if you did any study, this is like, yeah, this is like super easy. Like where like yeah. I guess these ones are kind of hard. I like how they didn't remove the. Is this like on the actual? Did they just not remove this? Huh. I didn't even realize that. That's funny. You can like the box of them like not yeah. But like these questions are kind of challenging, I think. The tracking the carbons, especially if they try and make you track it through the second cycle. Second cycle is weird. Yeah, the second cycle is really weird because like you have no idea. Yeah. Does this make sense? Yeah, you guys understand it though, like a decent at least a decent amount. I can like briefly cover it if you want me to like go over it a little bit. No, this one's just not served. Yeah, I can't zoom in anymore. Here, let me just download it and move it to my thingy so like you can actually look at it. Yeah, I would say like if you can get like the carbon cycling down, like that like immediately like removes like a level of stress that is just like present there. So here, okay, so and we all know the enzymes and what intermediates are produced here.
Put it down.
Okay, yeah. The sooner you memorize like what enzymes produce what, the easier like this stuff becomes, right? So like, um, for this, right, citrate synthase, right? This one's a conatase. This is isocitrate, citrate. Ah, dehydro. I'm just gonna say dehydro, right? Alpha ketoglutarate, AKG, dehydro, succinyl CoA, synthase or synthetase? What's the difference? Yeah, so why is it called synthetase and not synthase if it makes a GTP? Why is it called synthetase and not synthase if it makes GTP? ATP synthase is called ATP synthase and it makes ATP. Why isn't this called synthase? Yeah, it's called synthetase, yeah. Why is it called synthetase? There's a reason for it. It's still a triphosphate, right? It's because it was discovered in the reverse direction. So synthetase means use a TP molecule to make something else. But the direction they discovered the reaction in was this way. So it looked like they were using GTP to make this, right? But it's actually going in the other direction. It's stupid. Yeah, exactly. It's dumb. It's like, yeah, that's what I'm saying. Yeah. 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 So it's like because like no one calls ATP synthase ATP synthetase. Like so yeah, so it's some
But it can't go in the reverse.
yeah, it can, of course. Yeah, of course it can. Yeah, of course it can. Yeah. So succinate dehydrogenase, right? Fumarase, malate dehydrate. And then like what's produced from all of these, right? So what's produced from this step here? Nothing. So yeah, you're right. So isocitrate, but like no side products. I should have specified. Sorry. Yeah. So nice. No side products. This one and yeah, NADH. Okay. Next one. Yeah. So you should hopefully see a pattern here, right? Most of the dehydrates do both, but not always true. Some of them don't. Okay. What about this one? What goes in? Or sorry. What goes into this one? CoA. Yeah. I guess yeah, I probably should have said NAD plus goes into all the ones with NADH, right? You can't just make NADH without NAD plus. Yeah, I should have specified that, but here, let's go ahead. I'll put those in. I kind of assumed that we all we all kind of had that in mind, but I guess you're right. I probably should write that down. Yeah, just like magically you have NADH appearing without NAD plus. Yeah, I think I'd piss off a lot of people if I did that. Okay, and then this one produces GTP, like you said, right? And then it uses what to make it? GDP and PI, right? Yeah. The PI is an important part as well. Yep, CoA does come out, yep. I don't have space to write all this. But, and then CoA comes out, right? Yeah. And then succinate dehydrate does FADH2, right? Yeah. So remember that FAD goes to FADH2. I think the way I like to remember this one is like, and this is not like molecularly technically correct, but it's like no one cares about that. I think that for me, the easy way of remembering this was if you look at these two carbons, right? Notice how they both lose an H going here, right? That's how I remember it because it's FADH2. Yeah, because like, you literally lose an H2, right? So yeah, and then if we look at fumarase, what goes in, what comes out? Anything coming out? No. Yeah, good. Just water. Because believe it or not, the cell just does not have random hydroxides floating around, right? It's got to use water as a nucleophile. And then this last one up here. Yep, so NAD plus to NADH. Yep. And is there carbon dioxide release? No, right? Yeah, you can probably, yeah. they could ask that. It's a very positive delta G for this one.
That's what okay, it's possible juice.
Yeah, what goes in here? Acetyl-CoA. Yeah. For some reason, people like forget that acetyl-CoA goes in the first step. It happens a lot, actually, surprisingly. Um, yeah, I think it's just like people forget that like the cycle has to start somewhere, right? And like oxaloacetate obviously like doesn't have all the carbons, so but like if we do carbon tracking, for example, right? Where do the carbons from acetyl-CoA go onto this guy here?
Top two.
So the top two. So I'm actually going to label them in different colors here, so we can track them, right? If it is actually a decent use of our time. So I'll label this one in blue, right? And I'll label this one in green. Right? Okay, so let's go. So where are they showing up now in the Nikonatase? Say it, yeah. So are they showing like where which carbons are which?
Blue, green.
It's blue, green. Yep. So green, blue, right? Down here, stays the same, right? So blue, green. Down here, stays the same. Yep. Noticing a good old pattern here. Okay, where are they going here? Can't tell, right? So green could be here or here, right? And blue could be. Oh, sorry, I messed it up. Sorry, wait. Blue is here or here, and green is here or here, right? It's symmetrical, right?
Oh,
Right?
there's there.
Which two carbons? These two carbons, or
Yeah.
these get
The noise comes off, and then the
yeah. So this turns into this,
um,
right? But like because it's symmetrical, I don't know. Like the molecule like flips around all over the place, right? Like I have no idea. So it could be any of them. And then for this one up here and here, right? Here and here, and now you're here, and it's the same story. I have no flippin' clue. Even if I've added this OH, I have no idea, right? Right? Yeah, that's it. And so now if you can actually go down to if you go through the second cycle, it's a bit weird though, right? Because like in the second cycle, right? And this is gonna be really weird to draw actually. In the second cycle, where where are these carbons?
blue could be the actually the one in the middle, right?
This one or this one here? Yeah, it could, right? Yeah, so blue could be yeah, so it could be this one or this one, right? So blue, blue, and then where are the greens?
Cobalt.
Which carboxyls? Bottom one and this one. And so now if you try and look at the acetyl-CoA ones, it's these. And so like tracking through the second cycle is way weirder, right? Generally speaking, I think they usually only ask about the first cycle because I think it's a little bit easier to follow, and usually it's a bit more.
Oh,
You have no faith in this guy at all. Yeah. If it does, you gotta tell me, man. That's horrible. But yeah, I mean, and then like if you go back to this question here, where is it? Like for this, right? Indicate the label in the first cycle. So first cycle, first from glutamate to lactate. So we're going from glutamate, which is going to start here, right, to oxaloacetate, which is here, right? And so if we go here, these are all oxaloacetate, right?
oh,
So you're trying to figure out which version of oxaloacetate is going to be there, right? So if I label, um, I think which one does it say it labeled again? I think it labeled the. Oh yeah, so it tells you up here to determine the direction of metabolite flow using glutamate with the R group carboxyl. So you cannot forget your amino acids.
R group cobalt. Very well. So that means the side chain.
The side chain. Where is the side chain on this?
It's the CHCHCO. Wait.
Which one? This?
Yeah, that's
It is a sidechain. So you have to track these, right? And which yeah, so like I think it was tracking the specifically the carboxyl group, right?
Yeah, what?
Carboxyl carbon, which is specifically the COO carbon. So you're specifically tracking this top one. And we already did all the drawing for it, right? It's there, it's here, it's here, it's here, 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 and here. That's oxaloacetate.
Once and you can't tell, but you just say like 50% is the other.
Yeah, so let's go ahead and go down here. What percentage of it is going to be in this? No label. So, yeah, exactly, 0, right? This one? Yep. So you're saying it can be the top or the bottom, right? So 50%. Okay, this one here.
Wait, in the first
First cycle, remember, yeah, when we first cycle, right? Yeah. 0, 0. Yep. Yep.
right? Because it could be either.
Labeling both at the same time, though?
Wait, what?
Are they both going to be labeled at the same time?
No.
No.
How does you?
Well, they're not both going to be labeled at the same time, right? Only one's labeled at a time.
Also, so how much of both of them labeled is going to be in this, in like show up?
Yeah, it's like so like this for this one, right? You're saying that the oxaloacetate has 2 carbons that are labeled.
And that's not.
That's just not true, right? We only labeled 1 carbon.
Uh,
So these are the 2 positions, right, that it could be at, but they'll never both be labeled at the same time.
okay.
Because we know here, right? We only start with 1 label, right? The only reason it splits into 2 here is because we don't know which one it's on, right? It's not that there's 2 labels. We just don't know which one it's on, right? But like based off probability, right?
Yeah.
It's not that one of these carbons is more stable than the other, right? So that's why we're saying it's a 50-50. Because there's no impetus for it to go to one side versus the other side. Does that make sense? Right? So it's going to be 0 here because we can't have 2 labels, right? Unless we go through a second round, right? If you go through a second round and then add a label to acetyl-CoA, then you could have another label, right? And this is just some maniac stuff. You don't have 4 labels, right?
Why would I was thinking more like the possible carbons.
I think most people do when they look at these.
Shouldn't go like that.
It's yeah, it's one of those things where it's like so somebody who like does biochem, right? Like to them it doesn't seem like a trick question, and when you try and teach it to students, it's a trick question, right? Because like I when I first saw these, I was like, that's so weird, and then I've done it for like a year or two, right? And it's just like, oh yeah, that makes sense, right? But of course, it's gonna look really funny when you first look at it. So it's one of those things where I like. I'd be so surprised if this does not show up in some capacity on your exam. I'll be so honest with you. If this does not show up on your test, I don't know what they're doing.
Yeah, it's almost smart.
I'm waiting for them to do like a third cycle one. You know, like where's this carbon in the third cycle of this? Look at the fourth. What is the 10th cycle? Where would the carbons be in the 10th cycle? Gone. Yeah, they should be gone. They shouldn't be there, right? Because by that time, everything's like gone through like a shuffle like 8 billion times, right? And I honestly, I don't even know. I haven't done like all the tracking to figure out like how many cycles exactly it takes to remove a carbon. Because like like on the off chance that like, because we're assuming right that like on the off chance that this carbon right is the one that's labeled right, this carbon doesn't get deleted for like a while. You know what I mean? Like you have no idea. So I haven't like done like all of the possible combinations to say, oh, if you label this carbon, where is it going to go? Because if I track this carbon through the second cycle, right, it's here.
Yeah, they get
Exactly. They get towards being the bottom carbon, right? Yeah. So like this carbon, this carbon, this carbon, and then like, but now you're back at the same problem, right? If it's this carbon, I don't know if it's this carbon or this carbon. So we're back to being symmetrical, right? So it's like a massive rabbit hole. So I don't think they're not gonna test you past the second cycle.
Say
It could.
it just
It could just stay forever. Yeah, yeah. It could just like stay forever if you have like the exact lucky. Yeah, like the probability is like so low though, right? So that's why I'm saying they probably won't do that, right? As much as I'd like to demonize Harley here and say that he's gonna make like a really hard question.
is there a chance that I could stay in
Oh,
the
is there a chance? And the answer is yes. Yeah. But yeah, I think no. Um, does this stuff make sense to people? Like what's going on in this? Yeah, it's like another um
alternative options?
yeah. So like what would happen here to ATP production?
Smaller
Why is it smaller?
than just another optional.
Okay, well why does that make it smaller though? Just because there's another one of these, why does that make it smaller? Why is there less ATP production if that's smaller? Or if there's another oxidizing thing there?
It's because there's another route.
Yeah.
Pumping electrons.
So you're saying well, why are we not pumping electrons?
It's not reaching complex.
Complex 4 and 3. Right, yeah. Yeah. So how many electrons are actually how many electrons are if I go from here to here, how many electrons are going through? Just four, right? Because I'm only going through complex 1. What about FADH2? 0, yeah. He's screwed. It's 4 and 0, right? Right. So if they like if I do FADH2, it just goes here straight to here. There's nothing, right? So it's a 0 if I go FADH2 and only 4. How many ATP am I producing? With if I just have if I have one NADH and one FADH2 and they're going through AOX, how many ATP am I producing?
So does AOX stay one? Or does it just specify whether it's true?
Huh? Sorry?
There's nuance and two of us.
Yeah, right. It does because it goes from O2 to water, right? Yeah. So how many ATPs are how many hydrogens per ATP? So if 10 H plus
Right.
makes 2.5 ATP and 6 makes 1.5, what's the conversion here?
Or
4 for 1. So how many am I making if I have one of these and one of these? 1. 1 ATP. What if I quadruple this? What if I have 16 what if I have 16 going through here? 4, exactly right. Yeah, so it's not gonna change much, right? Okay, what's the difference? So if I put one NADH here, one FADH2, how does the product of in terms of ATP going through this pathway compare to this pathway? One NADH and one FADH2. No, before I was going through here, right? I want to know what's the difference between going through this pathway and going through this pathway, the normal one. The difference in ATP production.
wait, so you would still be producing like in the
In this pathway here?
yeah.
Yeah, of course, right? It's a probability game. What is the probability of it going to one or the other? There's no like it might be a bit like some other offset other than 50-50, right? But like it could still go to the other one. Yeah, I mean, I would assume if I'm making the very bold assumption that this has the same reduction potential as this, right? Then maybe I would say that like this wants to be reduced more than like complex 3, for example, right? Then maybe it's more favorable to go through this than this, right? But unless they tell me that in the question, I can't make that assumption, right? So my question still stands though, right? So if I have one FNADH and one FADH2, what is the difference in ATP production if I go through this versus the normal pathway?
The if you were doing lots, you'd only be making uh, for you can use it for hydrogens.
Mm-hmm.
Use it, of course, to make whatever make it. Take a beat.
So we're making how much ATP?
Hydrogen.
What's the relationship between hydrogens and ATP?
So okay, 14.5 is uh,
Yeah, I mean, so yeah, right. So 4H plus equals 1 ATP. This is like a general rule of thumb you can memorize if you want. Right. So you're saying that if we have one of each and we're going through this pathway, we make 1 ATP. Okay, what about if we go through the big pathway? Any other?
okay,
If we're going through the normal pathway, yeah.
then it'd be 1.5.
Yeah. So 4, yeah. So it'd be 4 ATP if you go through. What's the difference between the two? 3, right? And then you can do any multiple of that, right? They could do 5 NADHs and 5 FADH2s, right? Right? And notice how it's like multiplicatively scaled, right? If I multiply this by 5, right, this is 5 ATP, this is 20, right? So it like gets drastically worse as you add more electron carriers, right? Yeah, but like the thing, it doesn't change though. You know what I mean? Like it's the same thing. Yeah, it doesn't change if it's molarity or not. He just adds the molarity there to mess with your head, right? If I change this to 1 millimolar and 1 millimolar, it's still the same thing, right? So the only thing you need to worry about is like the unit is it millimolar, is it molar, is it micromolar, right? That conversion you still have to make, right? But other than that, the math is the same, right? They can't. There's really like there's only so much they can do with these before it like becomes repetitive over and over again. Um, but of course, they could just make up aliens and like say, oh, here you go, they have reverse electron transport chain. How does this work? Like they could,
When they first like
well, I mean, even plants is a little bit different, right? I could have a weird system where I use like O2 to make FAD, NADH and stuff like that, right? I guess that's like kind of what plants do, but like they can make up whatever they want. You know what I mean? Like my Gen Chem prof used to do that, just like make up random scenarios from like alien universes and just be like, wait, what? It's really, yeah. We've got like a couple minutes left. Um, any? Oh yeah, actually, let's do this real quick.
oh, I love that.
I actually got this wrong when I took my exam. Like, I was really sick when I took this, so yeah, yeah. I was really sick when I took this exam, so I was so sick. Yeah.
You got
I
7.
think no, not a 97. I definitely could have like gotten like all the points on this question though. I got like all the points on the other questions, like most of them, right? I can't remember where I missed questions on, I missed points on, but like this was a really frustrating one to miss points on, like really frustrating. But anyways, yeah, let's go through this, right? So, and it actually doesn't matter what factor I change this by, you should be able to answer it, right? If I said 6 moles of pyruvate, you should be able to answer it. Yeah, exactly, right? Yeah. So like you would do it for 1, right? Get your answer here, multiplied by 6.
Is it 2, 0, and 1?
So how many NADHs are produced if we have 1 mole of pyruvate? And
Oh,
block succinate dehydrogenase, right? And you might be right. I might have just said that to throw you off, but
no, no. I'm not so. So, technically, is assume way. 2, 0, 1.
201?
That is. Yeah, wait. Okay. Just kind of there. It's acetyl CoA name. And
Through which enzyme?
it's like
Yeah, pyruvate dehydrogenase makes 1 NADH, right? Yeah. Does it make FAD as well? What does FAD do in pyruvate dehydrogenase? Yeah,
Does it do something?
it does. What does FAD do in pyruvate dehydrogenase?
It's
It's a cofactor. It's a cofactor, right? No, it doesn't make it because it's not being used in the reaction. It's being replenished. Yeah, right? Yeah. So yep, so E3, right? E3 to regenerate the dihydrolip oil, right, does a oxidation on the arm, right? It is time to go. But if you were to do this, I think this would be 3, 0, and then 1, right? And then you have to multiply. So that would be 3 times this, 7.5 plus uh it's 8.5. Right? I think if I did that math right, yeah.
oh, I gotta explain that.
Yeah, yeah. I think it was 8, was it 8.5? I can't remember off the top of my head. Yeah. I can't remember. I think it'd be 8, I think I did that right, but
We gotta just that one. That was substituting.
yeah, right. So you gotta keep in mind like where you're starting and where you're ending, right? Because when I first read this, I actually didn't read this part right here, like where it's toxic dehydrogenase. Yeah. So I actually didn't read that because like I think I got this correct. I think I missed this and this. I mean I missed these two because I didn't read the question. So
Well, you really have this sound
yeah. Maybe yeah, okay, yeah, we're done, but maybe I'll go through maybe I'll go through exam 3 or like the 2023 exam for Monday. Yeah.
so sometimes
Yeah, I mean because it's an exam review, it's going to be like 30 minutes back, right? Yeah, I guess like yeah. If I really need to, I'll push it, but like I'm going to try and prioritize people who are actually here because like there are like 6 people who filled out the form and then like no one shows up, so I'm just like, okay. So why are you filling out the form if you're not
still on form.
No, I mean I could make another one, but I think people like I think the time is like set now. Like people come for my they come for the exam reviews to be fair.